Hello and welcome to our webinar Introduction to Aluminum Foundry Alloys. My name is Martin Hartlieb and you can find my email address at the end of this presentation, so if you have any questions, feel free to send me an email and I will get back to you as soon as possible. In this webinar we will cover the difference between casting and rod alloys, how does the Aluminum Association numbering system work, castability, what does that really mean for an alloy? What are the most common foundry alloys? The impact of each alloying element, and of course, what do impurities in foundry alloys mean and do? So what is the difference now between casting alloys and rod alloys? We could say that casting alloys are kind of an engineering compromise. But let's start with rod alloys. Well, they are designed to be rod, so they must be workable, and that's what's giving them their final properties. The mechanical properties are really obtained from a combination of chemistry of the alloy, including impurities, the DC casting or belt casting process, the hot and or cold rolling, extrusion or forging process, so the working of the metal, the forming, the final forming, which can be, for example, stamping or high-speed blow forming, superplastic forming, things like that. And then the heat treatment and aging during the paint curing or paint baking process in a car body, for example. Now with casting alloys, as I said, it's kind of an engineering compromise because the alloy must be castable to near net shape. So I'm going from liquid to solid in the final state with nothing in between. So I need fluidity. First of all, I need to fill the mold, and then I need to be able to feed it during the solidification. So I need good feeding behavior. I need resistance to hot tearing and hot cracking during the solidification. My mechanical properties, they're really a compromise between chemistry and impurities, heat treatment, careful part and gating design, so that means solidification control, and the local solidification rate, which gives me the microstructure. And we have seen that with higher freezing rate, I will get a finer microstructure, and that will give me better properties, especially ductility. And then control of the defect structure, because very few castings are 100% perfect. So now let's have a look at casting properties. The first law of materials engineering is the properties of any material are a direct function of the process used to produce that material. So it is very clear that laboratory specimens, they are not castings. There are ways to come relatively close to very similar properties, but it's not going to be the same. And separately, cast tensile bars, they're not castings either. You can simulate something relatively close to maybe somewhere in the casting, but it's not the casting itself. And even excised test bars are not a full casting. It's just one machined bar, and it's representative for that one specific region of the casting. You can't say those are the properties that I'm getting in the entire casting. So now let's have a look at castability. What is that? Well, we said it before. First of all, it has to be mold filling. I need to be able to fill the mold out, the cavity in the mold completely. So this is when we are completely liquid. So I need fluidity. Fluidity can mean flow length per wall thickness of the casting, for example. Once the cavity is filled, then I need to be able to feed. I need to be feeding the shrinkage and compensate that shrinkage. If I don't do that, if I can't do it properly, I will see porosity. We call this shrinkage porosity, and we can see up and top right, then I can get macro segregation. And if I have a hot short alloy and I can't feed it anymore and it shrinks and it's restrained in the mold, I can get what we call hot tearing. Now let's talk about fluidity. So what is the impact of each alloying element? Well, if we have a first look at silicon, because it's the most common alloy family, of course, the 300 series with aluminum and silicon and something else. So if I had just pure aluminum, I can see my fluidity would actually be really good. My properties wouldn't be that great, but my fluidity would be just fine. If I add silicon, my fluidity first goes down until I reach maybe 3-4%. That's when it gets the worst, and from there on, it gets better. And at the eutectic point, I have recovered very good fluidity already, but if I wanted to have the best fluidity, I would actually go to an 18% or so silicon level, which is exactly what we see in the typical hypereutectic alloys of the 390 family. If you look at magnesium, I see a very similar effect. First, if I add some magnesium, my fluidity goes down very quickly. If I wanted to go up to eutectic point, I would have to add 33%. So I would not have an alloy anymore. I would have some kind of mischmetal then. And if I wanted to get optimum fluidity, I would have to go to almost 40%. So nobody does that really. But if we look at copper, for example, we actually see a similar situation. If I add, I lose fluidity first until about 10%. After that, it goes up again, but the eutectic point again is pretty far out, so you won't see an aluminum copper eutectic alloy. If I put all of this together, what I could do now is make a graph like this and say, okay, I'm starting with a 0, that's my aluminum fluidity at a given temperature, and then I add every element and I see whether it improves or actually reduces my fluidity in millimeters in this case. So now that we covered fluidity, we have 4 different feeding mechanisms. The first one is quite obvious. As long as I pour the metal in, I have liquid feeding and I'm filling out the mold. And then when it slowly solidifies, usually away from the walls, I have mass feeding. And then I have the grains forming out, and then, well, it's called intergranule or interdendritic feeding. And then after that, I get into solid feeding, and that's an important part in high pressure die casting or squeeze casting, of course. Now, hot tearing, and that's a tricky thing. So everybody knows that when something is hot, it's bigger than when it's cold. And when metals solidify, it actually shrinks. And most aluminum foundry alloys shrink by 6, 7, 8% easily. So we would have to basically design a part that it can easily shrink by that amount, well, without being obstructed and causing it to crack. In an ideal scenario, I would just solidify it from one end to the other, and from where I'm feeding, it's still liquid, and on the other side, it's solidifying towards where I'm feeding. Well, in reality, that's not always the case. Very often, I might have a thick section on the other end of where I'm feeding, and in between, it's thinner, and I can't feed it through, and it's solidifying all over and at the same time. So that's when I often get these cracks, and that's during the solidification while the part is still really hot. And that's why it's actually called hot tearing. Now, castability of different foundry alloys, it's hard to just categorize it and give it a number, but a lot of people have tried that. And you can see here, and you can always debate whether this should be on a scale of 1 to 5. Should it be a 5 or a 4 to 5 or a 4? But in any case, a lot of people with a lot of experience have given input in such tables, and we can find them in the literature. And what's very easy to see is, okay, well, a 201 alloy, that's an aluminum copper alloy, and this one actually with a little bit of silver in it. So hot tearing would be 4 to 5. So it's very sensitive to hot tearing, but we can see it also is prone to shrinkage and to corrosion, but it's very easy to machine, for example. While an A356, everybody knows that, it's perfect for hot tearing. It's the most castable alloy. That's why we're using it so much. And it's pressure tight, very good fluidity, not so shrink prone. And depending on the copper level and nickel level that I have in terms of impurities, it can be very corrosion resistant. So like this, I have all the alloys somehow classified. But now I also have to look at comparative mechanical properties, because the first thing is I need to be able to to cast the part in my mold into the final shape that I want, but then I'm also looking at certain properties. So mechanical properties are usually the first thing we're looking for, and let's get started with A356 or 357 because it's the most common foundry alloys, as I said. I usually just say, okay, well, it's 30, 40, and then between 5 and 10% elongation. Or if you think in megapascal, well, 200 yield, 275 can be 300 tensile strength, 5 to 10% elongation. We will see this in other webinars as well. As soon as I go up in temperature, my strength goes down very quickly and my elongation goes up very quickly. So that is our baseline. So what else could we be looking for? Well, maybe we need really good corrosion resistance, much better than A356 is giving me. And maybe I need a certain property package where I don't need to go through a solution heat treatment process. Maybe I even want to anodize the part. Well, then I need a 500 series alloy. Well, the 535, if we compare it, interesting property package because this is an F in S-cast condition. I'm actually reaching 20 KSI, 140 megapascal yield strength, but I reach the same tensile strength as we had in A356 T6, and I have higher elongation. So 13% elongation, and that's not unusual for this type of alloy. So very interesting property package. Now, if I want to go much higher in strength, if I need to cast an aerospace casting or a high-strength suspension casting, well, the A206 alloy is an interesting option. Now, it might give me more problems with corrosion resistance, hot tearing, things like that, like we have seen before, similar to the 201 alloy. But if we look at the properties, well, I can be much higher in terms of yield strength in the T4, where I have high elongation, 17% elongation here, and 38 KSI yield. And in T7, I will lower the elongation to just 11.7%, but 50 KSI yield strength, 63 tensile strength. So very, very strong. And because it's aluminum copper alloy, it actually keeps its high strength at elevated temperatures as well. So that's a very interesting thing that we might need for many applications. Now, if high temperature strength is actually a big thing that I need and I don't care much about ductility, then I might even add a bit of nickel into it. So now we look at the 242 alloy, often used, for example, for aerospace cylinder heads or motorbike cylinder heads sometimes, things like that. I don't need elongation, but I need high strength at high temperatures, so I can see very quickly, okay, here I got 34 KSI at room temperature in terms of yield strength, and at 150 C, I still have 33. So this alloy, very temperature stable. And like this, I choose my property package depending on, well, what alloy can I cast for a certain type of application? What properties do I need? And, well, mechanical properties are obviously just one criteria, but there are many criteria that I have to fulfill, and in the end, I will come up with some kind of compromise. So when we look at casting properties, we see that castings very seldom, actually almost never, have one single set of properties. The properties depend on the microstructures, and therefore they are a very local phenomenon. Local solidification rate is interacting with gas stirred inclusions and all the things like that. So mechanical properties therefore have usually a mean and a certain variation, a certain spread in the casting. So we need design properties, and they must take both of those into account. So castings frequently have a time-based component as well, so they might even age over time and change their properties. Slow, gradual chemistry changes or even seasonal changes are possible. And of course, the first economic law of a casting is absolute perfection 100% of the time will cost an infinite amount of money. So let's have a look at the numbering system of our North American Aluminum Association. And I think a lot of you are familiar. There are two different numbering systems. One is the rod alloys, and they are usually 4 digits. So you might see a 6061 alloy or a 6082 alloy. And then you have the casting numbering system, and that's totally different. So we have 3 digits, sometimes a letter in front of it, and sometimes then something else behind it. So what's really in that numbering system? First of all, we have the family name. Let's say the typical ones are in the 300 series alloys, and therefore they start with a 3. And that really tells you something about the alloy. It tells you that, okay, if a 1, then it's a pretty much pure aluminum, 2 is aluminum copper, 3 aluminum silicon, plus it can be magnesium and or copper, and then 4 just silicon, 5 just magnesium, and so on. After that, you have the next 2 digits, and they are just kind of random. I mean, when people register the alloy, they will try registering maybe close to something that's similar, but that does not really tell you, okay, well, the 10s are with copper and the 20s are with just magnesium or something like that. It doesn't tell you exactly more about the chemistry. So it's basically a random number behind it. The first one who registers the alloy will just get a 3-digit number. So the first one who registered the 356 alloy, well, that was the 356. And the second one who registered another alloy that was very close to it, but not exactly the same, they will get an A in front of it. So there you had the A356. And if there's somebody else who comes and registers a similar alloy, same type, but a small modification to it, we'll get a B in front of it, and then a C, D, E, F, and so on. And then we have a dot, and we have another number behind it. So very important here, the dot 0 is the casting composition. So that's what we want to achieve in the casting after it's cast. So you got to subtract whatever you burn off in the process, and you have to add whatever you pick up in the process, like iron, for example. A dot 1 is an ingot specification. So usually you will see slightly higher purity in terms of iron and things like that you will pick up. And usually you will see a little bit higher strontium or magnesium or anything that you burn off. And some foundries will obviously burn off a little more or pick up a little more than others. And therefore we have also a 0.2, and 0.2 is then the higher purity specification. And then we will sometimes find a letter behind these numbers with a dot 0 or 1 or 2. And those letters mean, okay, so if I have an S behind it, then it's strontium modified. If it's N, then it's sodium modified, C with calcium, and P with phosphorus. So pretty simple. If we have a look at one example, I mentioned already before, 356, we have the dot 0, so silicon doesn't really change. You don't pick it up, you don't lose it. Always the same, whether it's in the casting or in a normal or higher purity ingot. Copper you might pick up, so the higher purity, the 356.2, has a lower copper than the casting specification. Magnesium you will burn off. Again, the ingot specification is higher in magnesium than the casting specification. Iron, the opposite, you will pick it up, and therefore the ingot specification is lower than the casting specification. So now let's have a look at the different series in our Foundry alloys, and let's get started with a 100 series. As I said before, that's pretty much pure aluminum, so at least 99% minimum is aluminum. The typical representatives here are 100, 130, 150, and 170. And they all have one thing in common, pretty high conductivity. Of course, it's pure aluminum. There is no strengthening element in there, so they are low strength but very high ductility, and they're pretty corrosion resistant, just as, well, pure aluminum is. And therefore, they are used for primarily electric motors. That's why we call them rotor alloys. They're also used for some bus bars, so electrical conductors, or decorative and artistic castings. Then we have the 200 series alloys, and they are exactly the opposite. They contain mainly copper. They were the first real alloy family that was created in aluminum many, many years ago, and typical representatives here are the 201 with silver, 203 with cobalt, 206 pure aluminum copper alloy, and 242 copper with a little bit of nickel in there. They all have in common high strength and fracture toughness. They're all heat treatable. They're Pretty difficult to cast, especially in permanent mold. Feeding can be difficult. Hot tearing is an issue. They're prone to shrinkage, prone to SCC, stress corrosion cracking, and especially at high copper, this is even worse, and with other elements like nickel. The high temperature strength and wear resistance gets pretty good, so that's why they are used primarily in high strength aerospace castings, speed brakes, thrust reversers, motorcycle and diesel and aircraft pistons or cylinder heads, and applications like aircraft generator housings. That's, for example, a typical one for the 242 alloy. I mentioned before 300 series, that's the workhorse of the foundry industry. It's kind of everything aluminum, silicon, and something else. So a lot of them are just aluminum, silicon, and magnesium. Some are aluminum, silicon, and copper, and some are with both. So aluminum, silicon, magnesium, and copper. They all have in common excellent castability. They're all heat treatable. As soon as you have strengthening element magnesium in there, you will get the mag silicide hardening, or with copper, we have also seen very heat treatable. You get very interesting property packages, and you can vary it depending on aging, for example, things like that. So you can really tune the alloy extremely well just with the chemistry and then the combination with heat treatment. And that series covers pretty much 90% of all castings made in North America. The 356 alloys are the workhorse of the foundry industry, and as you probably know, wheels are made from A356, so a relatively high purity, basically primary version of it, and engine castings are mainly made from the secondary 356 or the 319. A380 is the workhorse of the die casting industry, so you could say that's the most common foundry alloy in North America, but basically worldwide, with slight variances in other regions of the world, but it's basically the alloy that's made from 100% recycled content. So you can see things that do not need much ductility, like engine blocks, transmission cases, all sorts of brackets and things like that. It mainly goes into engine components, wheels, aerospace, structural castings, almost anything you can think of that doesn't have super special requirements, like it needs to be anodizable, or it needs to have super high strength, or it needs to be brazeable. So now let's get to the 400 series alloys, and they are a binary alloy. So if we have only two elements in here, so aluminum and silicon, then we're talking about a binary alloy. And most common variants are, of course, the 413. I think most people are familiar with that one, but then there are also 443 and 444. They are non-heat treatable. Well, you could heat treat, but it wouldn't give you anything, because without magnesium, just aluminum and silicon doesn't really do much. We see a lot of the 413 because it's near eutectic, so it has very high fluidity, and it can just have some solidification shrinkage and hot spots and thick walls. It has good ductility, but only moderate strength without the magnesium in there, but pretty good corrosion resistance and pressure tightness. So it's used, for example, for jar jet cooler housings and things like that. Any kind of intricate and thin-walled castings, some wheels even in Europe, the smaller wheels, smaller car wheels, architectural and ornamental castings, garden furniture, street lamp housings, electrical castings, lawnmower bases. I mean, you can see it's really a lot of different things, even some outboard marine pistons that are made from this. And then we get to the 500 series alloys, and they are aluminum and magnesium. Pretty much nothing else in there. It shouldn't be. Typical representatives are the 514 or 518, the 520, and the 535, also known as Almac 35. They all have excellent surface finish and corrosion resistance. That's why they are usually used. Good machinability, and they can be anodized, and that's the special thing. So if you're looking for an alloy that can be anodized, that would be the go-to family in our foundry alloys, and you will get moderate to high strength and toughness, but pretty good ductility, even without any heat treatment, but it's pretty difficult to cast. You will get high oxidation because of the high magnesium, so prepare yourself for a special melt treatment and or beryllium addition, which some people don't really like. We can find a lot of marine applications, therefore, of course, because of corrosion issues, but also hardware and ornamental applications, food and dairy processing, as well as chemical and sewage industry equipment, fittings, cooking utensils, optical equipment, name it, a lot of different things, even for computing, aircraft fittings, bridge post castings, and tire molds, and that's the 514. That's kind of a very special one. Now you could ask yourself, where is the 600 series alloys, because I'm going to skip that. Well, if you're interested, they are in Australia. There you can find them. That's the only region in the world that has a 600 series alloy. Now the 700 series alloys, that is the aluminum zinc family that might also contain magnesium. Typical representatives are 705, 7, 9, 11, 12, and 13, as well as 7, 71, and 72. They all have very good mechanical properties without any heat treatment, so that's why many people also refer to them as the naturally aging alloys. But they can be heat treated to actually very good mechanical properties. They have excellent surface finish and high dimensional stability. And we have the 712 alloy in here that is also brazeable. They're ideal for parts that require good strength or impact resistance. Furniture, some marine castings, farm machinery, machine tool parts, or molds for blow molding plastic bottles. You can even find some aerospace castings in 712 and 13. Last but not least, the 800 series, that's aluminum and tin, and to some extent copper and maybe even some silicon in there. The most common representative is of course the 850 alloy. There is also 851, 52, and 53. Now, tin is not soluble in aluminum, and that makes it so great. It appears as small droplets in the aluminum matrix. So, as tin is very soft, it's ideal for lubrication. It gives very good tribological properties, and the small amounts of copper and nickel are added to strengthen the aluminum matrix. It is therefore the ideal alloy for bearings and bushings. So now let's have a quick look at international numbering systems. There is unfortunately no real official international numbering system that everybody is referring to. Really, every country or every continent has a different one. Luckily, there are cross-referencing tables, and some of them can get really big, and sometimes not all of them really have an equivalent in other countries or regions. North American and Australian designations, they look very similar, but they are not the same, so be careful. If Australians talk about their three-digit number, that doesn't mean that is the one that you think of. Now let's have a look at Foundry alloys. First of all, we need to talk about alloying elements and impurities, the influence on properties, especially strength and elongation, toughness, corrosion resistance, conductivity. And the same element can be both. It can be an alloying element, giving it strength, and in a different alloy, it might be an impurity. The casting process and special requirements on the alloy, whether it's more or less forgiving. And then we need to talk about the phase diagrams. And here is one example for aluminum and silicon. And this would be a binary alloy phase diagram. So there are only two alloying elements, aluminum and silicon. If we're talking about three elements, then it is called ternary. And if it's for quaternary alloys. So here we can see the aluminum silicon phase diagram just between 0 and 20% silicon, which is where most of our alloys are. So we distinguish on top of the line, we have the liquid phase. We see the eutectic point at 12.7% silicon. Below the liquid and to the left of the eutectic, we will find liquid and aluminum. To the right, in the same triangle, we find liquid and silicon that solidifies first. If we fall below the 577C line, where the eutectic liquid is all frozen, we find aluminum and silicon, and this time now it's all solid. So if we look at the most important areas of this phase diagram, we can see between 5 and 8% silicon, we have the most common ones, the 356, but also 355, 319, 320. So most of the sand and permanent mold casting alloys. If we move more to the right, between 8 and 10% silicon, we find typical die casting alloys like 380, of course, but also 360 or 383. And then between 10 and 13% silicon, we find the close to eutectic alloys, so that would be the 336, 339, and of course the 413, which is pretty much a eutectic alloy. So we find piston and some die casting alloys. And then we have pretty much nothing until we get to far hyper-eutectic, so in the range of 16 to 20% silicon, and that's where we have the 390 type alloy with some variants like the 392, the Mercosil. They are used for high wear resistance. We see here a few example micrographs from the 4 region of the aluminum silicon diagram. On the left top, we see the A356 alloy. The light gray areas, those are actually the alpha aluminum. So this is pure aluminum that solidified first. You remember when we're falling below this curve, liquid, and then we have the alpha phase solidifying, and in this case it would be aluminum first. The other area that we can see here, the darker gray with a funny pattern there, this is now what we call the eutectic liquid. So this is a mix between aluminum and silicon, and in this case some magnesium and other elements in there. And we can see this has a very fine structure, so this is actually nicely modified eutectic. To the right, we see the 380 die casting alloy, and we see this looks not as nice at all. And we see big chunky dark parts in there, and we can see needle-like structures in there. So those are big intermetallics, iron needles, and all sorts of impurities that are in there, because this is a typical secondary die casting alloy. If we look down on the left side, we see a piston alloy, and you can just imagine that this is not an alloy designed for a lot of ductility. Just like the 380 die casting, we have a lot of elements in there that just make it strong and hard, but not very ductile. We don't have nice round shapes like on top. And then to the right, we see the Mercosil 392, and here we can see, of course, these darker gray spots. They are silicon, and as we've seen before in the phase diagram, here the silicon actually solidifies first as the alpha phase, and then the other elements are freezing after. So now let's have a look at the aluminum, silicon, copper, and some magnesium family. So that means the A380, the most common foundry alloy, the die casting alloy, and the 319 alloy. They are among the most widely used aluminum casting alloys. In fact, they represent probably easily 2/3 of the total foundry alloy market in North America. There are very different amounts of both elements, and some also contain some magnesium. Copper contributes here to the strengthening and the machinability. It of course also makes it strong at higher temperatures. That's why we can see those alloys used for a lot of engine castings. Silicon improves the castability and reduces hot shortness. And the aluminum, silicon, copper alloys with less than 5.6% copper are actually heat treatable. Although most A380 castings, of course, are not heat treated because they're die castings. There are many alloys of this family that are also contain some magnesium, which will improve their heat treatment response, giving us the maxillicide hardening, and many hyper-eutectic silicon alloys with 12 to 30% silicon. They also contain copper. The primary silicon phase imparts excellent wear resistance. We were able to see before in the microstructure, and the copper contributes to matrix hardening at elevated temperature. So we get high temperature strength combined with wear resistance. And that's what we see in the 390 or 391, for example. There are a multitude of applications, but a lot of them are precisely where we have exposure to high temperatures. So in powertrain castings and also, of course, many general purpose high pressure die castings. The aluminum silicon magnesium family, so that's the 356, 357 type. The advantages are, of course, moderate to high strength and ductility for structural components. So the magnesium lets us really tailor the property package. They give us excellent castability, largely immune to hot tearing and cracking. And they have a large volume fraction of eutectic, which allows us very good feeding. And there's largest database on mechanical performance of any casting alloy group. So it makes it very easy for a product designer to use one of those alloy types to design their parts. They also have high thermal conductivity in comparison to the aluminum copper or aluminum silicon copper alloy. That makes it very attractive for certain applications as well. And they have very good corrosion resistance because they have no copper in there or very low. It's just an impurity. They have good fatigue properties and machinability, but their disadvantages are they must generally be heat treated to achieve high strength and hardness. The large volume fraction of eutectic gives a microstructure that will always be a compromise and will always require careful control. So we have to add either strontium or sodium to modify it, or we need extensive thermal modification through heat treatment. The major uses here are really for A356, it's automotive wheels and suspension parts. The 357 types are usually aerospace castings that require higher strength. And we see all sorts of general and automotive structural parts. We can also see a lot of general purpose applications, for example, for street lamps, for all kinds of castings that have no other special requirements, like they have to be anodized or so. If we look at this family now in more detail, we see here two common representatives, the A356, and we see here again the chemistries for A356.2, 0.1 and 0.0. Remember 0.2 would be the high purity ingot, 0.0 is in the casting, and the F357, again the 0.2, 1 and 0. And we can see that the silicon is the same, and we have the magnesium as the major difference. A356 is the lower magnesium alloy, and 357 is the higher magnesium alloy. So that means in 356 I will get higher ductility, in 357 I will get higher strength. Now the major alloying elements are the silicon and magnesium, but also we need strontium for modification, titanium as a grain refiner. The major impurities are, for example, copper, and then iron, but also calcium and phosphorus. Specialties here are, for example, the F356 is actually a very low magnesium version of the 356 family for basically high ductility that's traded in for strength. Another oddity is the C356, and that is a premium low iron 356 variant, and the ingots are actually usually required to have below 0.04 iron. Related alloys here would be the 354 and 355. They add a little bit of copper, or the 360, which is a die casting variant. So now let's have a look at the role of each element. And let's of course start with silicon, as it's the biggest alloying element in all foundry alloys. Higher silicon content in the alloy means it promotes fluidity and castability, it reduces shrinkage, it improves hot tear resistance and feeding characteristics. It also increases strength and stiffness even on its own. It reduces the specific gravity and the coefficient of thermal expansion. It improves pressure tightness and corrosion resistance of castings, and in hyper-eutectic alloys, so above the 12.7% eutectic point, it is used to increase wear resistance. Most die casting alloys are usually in the 8 to 13% range, and most sand and permanent mold casting alloys are in the 5 to 8% silicon range. Now, there are diagrams that really show all the different effects of each element, and here for silicon we can see that. So fluidity, feeding behavior, shrinkage sensitivity, the uniformity of shrinkage and hot tear tendency. So if we look at one specific point, like here somebody looked at the 13% or 14%, so slightly above the eutectic, and we can see, okay, the fluidity, that is our A here, that went down first, and now we're pretty high up again, so not at 390 level, but very decent. And I can look at all the different characteristics that I would typically be looking for in a foundry alloy. In aluminum silicon alloys, magnesium is used for strength and hardness, especially after heat treatment. It actually gives us the heat treatment response in the alloy. If I have aluminum and silicon as binary alloy, I will not get really a heat treatment response. So the Mg2Si, or mag silicide base precipitation hardening, displays useful solubility limit of approximately 0.7% magnesium. After that, it doesn't really do anything anymore. It actually softens the matrix. So that's why usually we see most alloys specified up to 0.6% magnesium. It was also found that in aluminum silicon alloys, higher magnesium content reduces the corrosion resistance slightly. So you have to be careful with that. And precise control improves chip formation and removal in machining operation. Now, if we look at the aging response, you can see this very nicely here, that with increasing magnesium content, if the magnesium content is low in F-temper, the aging response isn't much. We can see here increasing magnesium does a little bit, and we're just looking at very low contents up to 0.1%, but see that at 120 C for 1000 hours, so over time, so it would age naturally, or if we go to a higher temperature, we can artificially age, and we can see that really as soon as I surpass the, here we say 0.06%, I would say 0.05% approximately, we see very quickly the yield strength goes up. So that shows us the heat treatment response coming from the mag silicide hardening. Now, if you look at the role of magnesium in aluminum magnesium, the 500 series binary alloys, there it actually gives us excellent mechanical properties, especially high ductility as cast. So no heat treatment needed, wouldn't really do that much. And as cast, very nice property packages. I especially get very nice physical properties and very nice finishing characteristics. So usually we will pick a 500 series alloy if I want to polish or anodize the part. They also machine very good. They show excellent corrosion resistance, and usually it's more difficult to cast than any 300 or even the 400 series alloys, at least at the typical current levels. Relatively poor fluidity and high solidification shrinkage. We also need to make sure we have special handling and control the selective oxidation of the magnesium phase when in the liquid condition. So therefore, very often beryllium is added into these alloys. Now, if we look at the role of copper, so we can find this, of course, in the 200 series alloys as the main alloying element, but also in some of the 300 series alloys. It's usually a strengthening element, especially at elevated temperatures. Otherwise, I only need it if I want to go to very high strength in the 200 series. It provides solid solution strengthening and creates age hardening effect through the aluminum copper precipitate. It increases hardness and density. It improves machining characteristics as well. It actually reduces shrinkage, but also ductility and corrosion resistance. That's why it is usually in 300 series a problem for any application that needs to be corrosion resistant and is therefore minimized. Lower content means it imparts higher general atmospheric corrosion resistance. Copper also needs to be limited in structural castings if they are welded, because as soon as you go beyond 0.3 or some would say 0.35% copper, you get into trouble when you try fusion welding the parts. Now let's have a look at zinc as alloying element, as we can find it in the 700 series alloys. Zinc has actually a very wide solid solubility range in aluminum. It can provide solution strengthening effects at higher concentration, but excessive amounts are actually not really good and cause cracking. And we see this sometimes, for example, in an A380 alloy zinc is not an alloying element, but is limited to 3%. So if I'm actually high in silicon and in copper already, so I have a very strong alloy and now I'm adding 3% zinc, I might actually just crack the casting right before it comes out of the die. Zinc can improve machinability, and in small amounts, up to 0.2 to 0.3% in the aluminum silicon magnesium alloys, zinc has actually very little effect in most alloys, but if you go a little higher, and we see some alloys with 0.5 to 0.85%, it is used as strengthening alloys in combination with special heat treatments. But we can find some problems if we're trying to bond these castings with other components. When I talk about special heat treatments here, you have to think about not the usual single or two-stage heat treatments, solution heat treated at 520 degrees followed by artificial at 180 degrees Celsius or something like this. Here we're talking about several more stages. So you might have solution heat treatment at 2 different temperatures and then aging again at different temperatures for different times. So you really need to know what you're doing here, and it takes a lot of fine-tuning to achieve the response that you would like to get. Now, in combination with copper or magnesium, it can result in attractive heat treatable and natural aging compositions. But in this case, silicon is the impurity, so we need to keep it very low. And zinc is also said to enhance surface corrosion, so sometimes it is added a little bit to prevent deeper corrosion, like filiform corrosion. Just give the aluminum its natural corrosion oxide layer on the surface that prevents any kind of harmful deep corrosion. So now let's talk about iron, and there are actually aluminum iron alloys that use it as an alloying element. You pretty quickly get to the eutectic point. I think it's around 1.6%. But really in most other alloys, and pretty much all other alloys, it is just an impurity and has to be limited. But it helps reduce die soldering and die casting. That's where you can find most of the iron. So most die casting alloys will be at 1 to up to even 1.3% iron. But we know it impacts negatively ductility. Iron improves fluidity and hot shortness, and this effect is even stronger the slower the solidification rate of the casting processes. So aerospace casting alloys, you will find a lot of them specified with, let's say, a 0.06 iron max to achieve very good properties, especially elongation. And permanent mold, let's say the typical wheel alloy A356, will be specified with ingots at 0.12 max. If you look at high integrity die castings, because they freeze so quickly with very thin walls, they can tolerate easily up to 0.25% iron. Iron also improves fluidity and hot shortness, and as I said before, this is used in certain alloy types that use iron as an alloying element. Here we can see a very nice example, or an extreme example I should say, of iron in a die casting alloy. You probably recognize this. It looks similar to what we've seen before. It's an A380, very high iron level, and I have seen 380 die casting sometimes with up to 3% iron, because very few die casters actually use a spectrometer to check it. This was just cast, and we can see the crack is along these iron needles, well, which are actually platelets in 3D. And so if you have any stress riser, and the crack will just go straight through your casting. If we look at what iron really does, a lot of studies have been made, and I'm showing here a picture from Jeff Sigworth's study, a couple of years old, but that was very nice demonstration, and we can see it started with 0.5% iron, and we have of course a trade-off between elongation and strength, so we move up the curve depending on how long we age, and we see we are on one curve and we just have this trade-off. If we want to move up and go to a higher curve, we have to reduce the iron. And we can see that already a reduction to 0.30 moves the curve quite a bit. And then we see another nice move going to 0.15, and then another big move going to 0.03% iron in the same type of alloy. If we look at iron as alternative eutectic alloy, we can see this here, and really the strength is not coming from iron. Iron is just used here to make it very castable, but the strength is coming from the magnesium. We see it's about 4 to 4.5% magnesium. Silicon is now an impurity and has just a maximum, and so is pretty much everything else. So the only other element we have in there is titanium as a grain refiner. And we have beryllium for oxidation of the magnesium. So now let's have a quick look at manganese. Manganese is used in, of course, the rod alloys, in the 3000 series alloys, but in casting alloys it's mainly used in die casting alloys or in secondary alloys, aluminum silicon alloys, and there it is usually added as half of the iron content. In die casting it is used to reduce die soldering and replace iron for higher ductility. Manganese has a limited solid solubility in liquid aluminum, but is actually higher than iron, and the higher solubility in aluminum gives us reduced tendency to form brittle faces and helps improve the properties. It typically is used to correct the iron intermetallic phase, and it's used to minimize die soldering, as I said. Some claim that over 0.5% beneficially influences internal casting soundness, but mind that you then run the risk of more sludge formation. So here we see a typical microstructure. We see the alpha aluminum, the light gray islands surrounded by the eutectic liquid, as we have seen it before, and then we see these needle-like structures in between, and those needles, they are bad for ductility especially, so we call them iron needles, FeSiAl5, and that is beta iron, and therefore what we want to do is add the manganese, and what we can see on the right side here is we have converted these needles into what we call Chinese script, so now it is alpha iron. So now there's a lot of interaction between iron and manganese, and we have to watch out when we add those two elements. And we already know a sludge factor, so manganese goes in with a factor 2 of iron, so we have to be careful how much manganese we can add. But then there's another factor, and that is whether we create large primary crystals, and they would also be bad. So we look at iron content and we look at silicon content. So we see here on the left side this blue curve, it's going up. So the more silicon I have in there, the more iron content I can tolerate without forming these large primary crystals. But this blue line actually goes down the more manganese I am adding, and therefore if, for example, I am adding 0.6% manganese and I am at, let's say, 10% silicon content, I can go over to the left and I see, well, I really should be well below the 0.2 iron content. So if we plot that iron solubility against the manganese content, we can see here on the right side, and pretty much all the typical structural die casting alloys are just below this curve. So we want to be relative close to it. We want to have enough manganese to beat die soldering and not get into die sticking issues. We do not want to get much beyond it to get sludge formation, and we want to avoid the formation of these large primary crystals. If we look at the role of other elements, well, of course, titanium. Titanium is used as a grain refiner in many foundry alloys. It's often in combination with small amounts of boron, typically 5:1, and you will hear that very often, Tibor grain refiners. And then we have chromium. Chromium is not a very popular element that we want to add, but it is added in 700 series alloys to improve corrosion resistance. It can also help modify iron needles and beat die soldering in high pressure die casting, but watch out, it is actually even 3 times more than iron when it comes to sludge formation, so we really want to limit this. And then we have nickel, and nickel, of course, we know it is added in combination with copper, usually to improve elevated temperature properties, and as that it is very good. High temperature strength, so for example in the 242 alloy. It is also used in piston alloys, But watch out, nickel is causing filiform corrosion, so the corrosion that goes deep into the casting, and that already happens if it gets above 100 ppm, so at a very low level. So it's therefore treated in most alloys as an impurity and has to be minimized. So now let's have a look at modifiers, and of course I have to start with strontium because it is the most common silicon eutectic modifier that is used in our industry. Using a chemical modifier is improving ductility of the alloy. We can also thermally modify the alloy, but then we would have to heat treat it longer, which can cause other problems and of course is expensive. It was also found to help beat die soldering and die casting, and higher levels are often associated with porosity and thicker section of castings, and especially in processes with slow solidification rates. So that's why you often find precision sand casters who do not want to have strontium modified alloy for their castings. But others say, well, it helps disperse porosity and convert macro into micro porosity, which then again is more positive. One problem with strontium, that will be the same with sodium, of course, is it burns off very quickly. And we can see here on the right, the graph, it shows starting at 240 or 250 ppm, which is a typical level that you will find in an ingot. And you can see that already after a relatively short period of time, it goes down. Now, I have to say that this burn off is much, much faster if you have the melt surface exposed to air, if it can react with oxygen, and especially if you're stirring it. So if you are working with higher strontium levels or you're concerned that you're burning off too much, what you need to do is you cover it, maybe have continuous degassing on so you have a controlled atmosphere on it, and do not stir it. I have actually done trials with elevated strontium levels as high as 1000 or 2000 ppm, and we were able to keep them pretty stable even during the night and for, let's say, almost 24 hours with minimum loss if you really cover it all the time and you do not stir it. As soon as you open it and you start ladling out of that furnace, it drops like a rock. And then we have, of course, sodium, and we can see here, now we're talking about minutes held, and we start at 30 ppm, and you can see after just 20 minutes, you already lost at least half of your sodium. So that's why it is not that common. But it is a very good modifier for aluminum silicon eutectic. It can embrittle the aluminum magnesium alloys. Because of the rapid fading, really, it's not typically used. And then we have phosphorus, and of course phosphorus would be a very good modifier. It's typically only used for hyper-eutectic alloys. And there it works very well, and we have to really watch out because it negatively impacts, it actually destroys the effect of both strontium and sodium on eutectic modification. So if we recycle parts that were phosphorus modified, then we should not mix them with other parts that will be or are strontium modified, because this will just cancel itself out. Now let's talk about dispersoid hardeners, and the first ones, of course, vanadium and zirconium. We see them in some of the high temperature alloys, for example cylinder head alloys, and they have chemical properties very similar to titanium, and typical concentrations in casting alloys are very, very small, so below 50 ppm for zirconium and below 200 ppm for vanadium. There's no appreciable effect on mechanical properties observed when they're at that level. Both lower electrical conductivity, and really, if you want them to have an effect of dispersoid hardening and therefore strengthening the alloy, you have to be above 0.1%. I see most alloys using them at 0.14, 0.15%. And both are also used in combination and also enhanced, for example, by manganese. And then we have molybdenum, which is virtually insoluble in solid aluminum, but has very limited solubility in liquid aluminum. It forms intermetallic compounds with aluminum, the Al10MO and Al5MO, during the solidification. So it is again used as a dispersoid hardening, strengthening agent. And unfortunately, normally it's pretty much at the same price as vanadium and zirconium, so all these elements are pretty expensive. But If we talk about expensive, nothing compares to scandium. I've heard the global scandium market is only about 150 tons per year, so it's obviously an element that is quite rare, and you usually don't want to use it. It is used in certain aluminum alloys, in certain rod alloys. It has actually tremendous effects. It inhibits recrystallization. It's a strengthening agent without penalizing ductility. It's a grain refiner and modifier of cast structures at the same time. So it really does a lot of good things, but even in small amounts, it makes the alloy pretty much prohibitive from a commercial point of view. Now, other impurities, of course, we talked about iron. It forms the iron needles, so we have to minimize it. And manganese can correct it at half of the iron content. Calcium is a weak eutectic modifier for aluminum silicon alloys, but it increases hydrogen solubility, so it actually leads to real increased porosity, and it reduces the surface tension of hydrogen bubbles, so it even makes them look bigger and appear bigger when you look into the casting, whether it's with X-ray or you cut them up. And then we have lithium, and we also want to limit that. Usually it encourages buildup in deposits in aluminum transfer system and dip tube plugging in upstocks and pumps. So in low pressure systems, it's really bad and needs to be minimized again. And then we have already seen phosphorus because it counteracts the sodium and strontium modification, and it makes the metal appear more prone to shrinkage. Therefore, we really want to limit all those impurities. Other examples, antimony, and this would be another nice modifier for the silicon eutectic, and it doesn't fade, so that's why it has been used, or was used in the past mainly, in certain French and Japanese alloys, even in some wheels that we can still find in the North American market, so you better want to separate them out. It reacts with sodium and strontium to form cores into metallics with adverse effects on castability and eutectic structure, so it's actually what we call a modification poisoner. Chemical analysis is pretty difficult because its spectrum overlaps that of iron, so if we have a spectrometer and we want to analyze for it, we might often not even see it. It's also classified as a heavy metal with potential toxicity. And then we have beryllium, and I mean, we have been using beryllium without any problems for decades, but it is used normally just in high magnesium alloys, so it's not a commonly used element in many alloys, not in the most of the 300 series alloys, but it's used to reduce oxidation losses. What was found then at one point in time that you can develop berylosis upon exposure to beryllium fumes or smoke and dust. You have to be careful, especially when you're melting, of course, the melt handling, and then blasting, machining, welding, or hand polishing the surface of castings that are containing beryllium. So with this, we're coming to the conclusions for this webinar. We have seen there is a very large variety of foundry alloys that can offer very, very different sets of properties, not just mechanical, but in general. Different processes will require or even allow us using different alloys, and we have seen the nomenclature is different around the world, so watch out when you talk to an Australian who might use an alloy name that sounds familiar to you, but it might mean something completely different. Alloying elements can have very different effects, and they can either be an important alloying element in one alloy, and it can be an impurity in another alloy. Now, certain elements are just harmful impurities in foundry alloys, and they must be controlled, they must be limited, and it is very important to source quality foundry ingots in the right chemistry if you want to make quality castings. We're coming to the end of our webinar. If you have any questions, here's my email address and G. Armstrong's email address. So if you want more information, need anything else, please get in touch with us. Thank you very much, and I hope to see you soon in another webinar.